LIN is a serial network protocol used for communication between components and vehicles. The need for a cheap serial network arose as the technologies and the facilities implemented in the car grew, while the CAN bus was too expensive to implement for every component in the car. European car manufacturers started using different serial communication topologies, which led to compatibility problems. In the late 1990s, the LIN Consortium was founded by 5 automakers, with the technologies supplied from Volcano Automotive Group and Motorola. The first fully implemented version of the new LIN specification was published in November 2002. In September 2003, version 2.0 was introduced to expand capabilities and make provisions for additional diagnostics features. LIN may be used also over the vehicle's battery power line with a special DC-LIN transceiver. Network topology. LIN is a broadcast serial network comprising one master and typically up to 16 slaves. All messages are initiated by the master with at most one slave replying to a given message identifier. The master node can also act as a slave by replying to its own messages. Because all communications are initiated by the master, it is not necessary to implement a collision detection. The master and slaves are typically microcontrollers, but may be implemented in specialized hardware or ASICs in order to save cost, space, or power. Current users combine the low-cost efficiency of LIN and simple sensors to create small networks. These subsystems can be connected by backbone network. Overview: the LIN bus is an inexpensive serial communications protocol, which effectively supports remote application within a car, a Euro unregistered trademark S network. It is particularly intended for mechatronic nodes in distributed automotive applications, but is equally suited to industrial applications. It is intended to complement the existing CAN network, leading to hierarchical networks within cars. In the late 1990s, the local Interconnect Network Consortium was founded by 5 European automakers, Volcano Automotive Group and Freescale. The first fully implemented version of the new LIN specification was published in November 2002 as LIN version 1.3. In September 2003, version 2.0 was introduced to expand configuration capabilities and make provisions for significant additional diagnostics features and tool interfaces. The protocol, a Euro unregistered trademark S, main features are listed below: single master, up to 16 slaves. This is the value recommended by the LIN Consortium to achieve deterministic time response. Slave node position detection allows node address assignment after power-up. Single-wire communications up to 19.2 kbits at 40-meter bus length. In the LIN specification 2.2, the speed up to 20 kbits. Guaranteed latency times. Variable length of data frame. Configuration flexibility. Multicast reception with time synchronization, without crystals or ceramic resonators. Data checksum and error detection. Detection of defective nodes. Low-cost silicon implementation based on standard UART-SCI hardware. Enabler for hierarchical networks. Operating voltage of 12 V, data is transferred across the bus in fixed-form messages of selectable lengths. The master task transmits a header that consists of a break signal followed by synchronization and identifier fields. The slaves respond with a data frame that consists of between 2, 4 and 8 data bytes plus 3 bytes of control information. LIN message frame. A message contains the following fields: synchronization break, synchronization byte, identifier byte, data bytes, checksum byte, frame types, unconditional frame. These always carry signals and their identifiers are in the range 0 to 59. All subscribers of the unconditional frame shall receive the frame and make it available to the application. Event-triggered frame. The purpose of this is to increase the responsiveness of the LIN cluster without assigning too much of the bus bandwidth to the polling of multiple slave nodes with seldom occurring events. The first data byte of the carried unconditional frame shall be equal to a protected identifier assigned to an event-triggered frame. A slave shall reply with an associated unconditional frame only if its data value has changed. If none of the slave tasks responds to the header, the rest of the frame slot is silent and the header is ignored. If more than one slave task responds to the header in the same frame slot, a collision will occur, and the master has to resolve the collision by requesting all associated unconditional frames before requesting the event-triggered frame again. Sporadic frame. This frame is transmitted by the master as required, so a collision cannot occur. The header of a sporadic frame shall only be sent in its associated frame slot when the master task knows that a signal carried in the frame has been updated. The publisher of the sporadic frame shall always provide the response to the header. Diagnostic frame. These always carry diagnostic or configuration data and they always contain 8 data bytes. The identifier is either 60, called master request frame, or 61, 0x3d, called slave response frame. Before generating the header of a diagnostic frame, the master task asks its diagnostic module if it shall be sent or if the bus shall be silent. The slave tasks publish and subscribe to the response according to their diagnostic module. User-defined frame. These can carry any kind of information. Their identifier is 62. The header of a user-defined frame is always transmitted when a frame slot allocated to the frame is processed, reserved frame. These shall not be used in a LIN 2.0 cluster. Their identifier is 63. LIN hardware. The LIN specification was designed to allow very cheap hardware nodes being used within a network. It is a low-cost, single-wire network based on ISO 9141. Inter-DAR Euro unregistered trademark S-car networking topologies, microcontrollers with either UART capability or dedicated LIN hardware are used. The microcontroller generates all needed LIN data by software and is connected to the LIN network via a LIN transceiver. Working as a LIN node is only part of the possible functionality. The LIN hardware may include this transceiver and works as a pure LIN node without added functionality. As LIN slave nodes should be as cheap as possible, they may generate their internal clocks by using RC oscillators instead of crystal oscillators. To ensure the baud rate stability within one LIN frame, the sync field within the header is used. LIN protocol. The LIN master uses one or more predefined scheduling tables to start the sending and receiving to the LIN bus. These scheduling tables contain at least the relative timing, where the message sending is initiated. One LIN frame consists of the two parts header and response. The header is always sent by the LIN master, while the response is sent by either one dedicated LIN slave or the LIN master itself. Transmitted data within the LIN is transmitted serially as 8-bit data bytes with one start and stop bit and no parity. Bit rates vary within the range of 1 kbits to 20 kbits. Data on the bus is divided into recessive and dominant. The time normal is considered by the LIN master's stable clock source. The smallest entity is 1-bit time. Two bus states a sleep mode and active a are used within the LIN protocol. While data is on the bus, all LIN nodes are requested to be in active state. After a specified timeout, the nodes enter sleep mode and will be released back to active state by a wake-up frame. This frame may be sent by any node requesting activity on the bus, either the LIN master following its internal schedule, or one of the attached LIN slaves being activated by its internal software application. After all nodes are awakened, the master continues to schedule the next identifier. Header. The header consists of 5 parts. The break field is used to activate all attached LIN slaves to listen to the following parts of the header. It consists of one start bit and several dominant bits. The length is at least 11-bit times. Standard users of today are 13-bit times, and therefore differs from the basic data format. This is used to ensure that listening LIN nodes with the main clock differing from the set bus baud rate in specified ranges will detect the break as the frame starting the communication and not as a standard data byte with all values 0. Sync. The sync is a standard data format byte with a value of hexadecimal 0x55. LIN slaves running on RC oscillator will use the distance between a fixed amount of rising and falling edges to measure the current bit time on the bus and to recalculate the internal baud rate. Inter-byte space. Inter-byte space is used to adjust for bus jitter. It is an optional component within the LIN specification. If enabled, then all LIN nodes must be prepared to deal with it. There is an interbyte space between the break and sync field, one between the sync and identifier, and one between every data byte in the payload. Identifier: the identifier defines one action to be fulfilled by one or several of the attached LIN slave nodes. The network designer has to ensure the fault-free functionality in the design phase. If the identifier causes one physical LIN slave to send the response, the identifier may be called a RX identifier. If the master's slave task sends data to the bus, it may be called TX identifier. Response space: response space is the time between the identifier field and the first data byte which starts the LIN response part of the LIN frame. When a particular LIN frame is transmitted completely, header plus response, by the LIN master, the LIN master will use the full response space time to calculate when to send the response after sending the header. If the response part of the LIN frame is coming from a physically different slave node, then each node will utilize 50% of the response space time in their timeout calculations. Response: the response is sent by one of the attached LIN slave tasks and is divided into data and checksum. Data: the responding slave may send 0 to 8 data bytes to the bus. The amount of data is fixed by the application designer and mirrors data relevant for the application which the LIN slave runs in. Checksum: there are two checksum models available within LIN. The first is the checksum including the data bytes only, the second one includes the identifier in addition. The used checksum model is predefined by the application designer. Slave node position detection, that is, auto-addressing. These methods allow the detection of the position of slave nodes on the LIN bus and allow the assignment of a unique node address. Allows similar or the same devices to be connected on the bus without end-of-line programming or connector pin programming. Restrictions: all auto-addressing slaves must be in one line, standard slaves can be connected in any way. Extra wire daisy chain: each slave node has to provide 2 extra pins, one input, D1, and one output, D2. The first SNPD node input D1 is either set to GND or connected to the output of the master. The output of the first node, D2, is connected to the input, D1 of the second node, and so on, resulting in a daisy chain. Each configuration pin DX has additional circuitry to aid in the position detection. Switchable resistive pull-up to VBAT, pull-down to GND, comparator reference to VBAT/2, XWDC auto-addressing procedure. At the start of the procedure no SNPD devices have a NAD assigned. 1 First auto-addressing LIN message, 1.1 All outputs are set to a high level, all pull-downs are turned off. 1.2 The first SNPD node is selected. It is identified by having the input D1 low. 1.3 The selected node takes the address from the LIN configuration message. 1.4 The detected node turns on the pull-down at the output D2, 2 Subsequent auto-addressing LIN messages. 2.1 The first non-addressed SNPD node is selected. It is identified by having the input D1 low. 2.2 The selected node takes the address from the LIN configuration message. 2.3 The detected node turns on the pull-down at the output D2. 2.4 Steps 2.1 to 2.4 are repeated until all slave nodes are assigned an address. 3 All pull-ups and pull-downs are turned off, completing the addressing procedure. Bus shunt method: each slave node has 2 LIN pins, bus in, bus out. Each slave node needs some additional circuitry compared to the standard LIN circuitry to aid in the position detection. The standard pull-up must be switchable to a mega current source from VBAT, shunt resistor, differential amplifier, analog to digital converter, BSM auto-addressing procedure. At the start of the procedure, none of the SNPD devices have a NAD assigned. The auto-addressing routine is performed during the sync field. The sync field is broken into 3 phases: 1 Offset current measurement, 1.1 All outputs pull-ups and current sources are switched off, 1.2 The bus current is measured, I offset, 2 Pull-up mode, 2.1 Pull-ups are turned on and current sources remain off, 2.2 The bus current is measured, IPU, 2.3 nodes with II equals IPUI offset less than 1 mA are selected. 3 current source mode. 3.1 selected nodes switch current source on and others switch pull-ups off. 3.2 bus current is measured. ICS. 3.3 node with II equals ICSI offset less than 1 mA is detected as the last node. 3.4 current sources are switched off and pull-ups are switched on. 3.5 The last node will accept the address contained in the LIN configuration message. This technique is covered by the patents EP 1,490,772b1 and US 7,091,876. LIN advantages: easy to use, components available, cheaper than CAN and other communications buses, harness reduction, more reliable vehicles, extension easy to implement. No protocol license fee required. LIN is not a full replacement of the CAN bus. But the LIN bus is a good alternative wherever low costs are essential and speed bandwidth is not important. Applications: LIN API. The LIN application programming interface provides a given set of function calls which have to be implemented within each LIN software driver. Using this predefined set of driver routines, all LIN functions may be accessed. The usage of API-compliant functions eases the implementation of standard software drivers. Also, the testing is sped up. Development tools: when developing and/or troubleshooting the LIN bus, examination of hardware signals can be very important. Logic analyzers and bus analyzers are tools which collect, analyze, decode, store signals so people can view the high-speed waveforms at their leisure. See also, list of network buses, references. External links: LIN Consortium. It is not longer available, because the latest LIN specification is being transcribed to the ISO as part of the process to be accepted as ISO standard ISO 17987 Part 1-7. CAN LIN training, brief CAN LIN background information, article about a free open hardware software implementation of the LIN protocol, an open-source Arduino-based LIN protocol analyzer, a LIN to RS-232 or USB data converter analyzer.